Hi everybody, so today we are going to talk about something called redox. Now this is part of what you already have learned and then we're going to build on it. So we're going to do a quick review of what you already know. Remember that octet rule? Of course you do. So oct means 8. So the octet rule says that all atoms want to have 8 valence electrons. That's called an octet. So the dream of every atom is to get 8 valence electrons. The reason why is this makes them feel like a noble gas, and so they are stable. So every atom tries to get 8 valence electrons, but not all atoms have 8 valence electrons. So if you are not a noble gas and you don't have 8 valence electrons, you still really want them. So you become an ion. An ion is a charged particle that has changed the number of electrons to achieve an octet. So we already learned our pattern of oxidation states that tell us about those ions. Everything in group 1 becomes a +1 ion so that it can follow the octet rule. Group 2 becomes a +2 ion. And then our pattern continues over here. We have +3, plus or -4. We'll talk about that. And then it flips, -3, -2, -1, and 0. In the middle, our transition metals don't follow a predictable pattern, but we're going to talk about what happens there. So we have 2 different ions that can form. So we have cations that have positive charges. Remember that T in the middle of cation looks like a plus sign, so that's how we can remember that. And the other option is that we can have anions with a negative charge. The way that cations become positive is when they are metals that lose electrons. So cations are metals that lose electrons. Anions are nonmetals that gain electrons. That's all stuff that we know. All we're going to do today is assign new names to that process. So we say that something undergoes oxidation when an atom loses electrons. Okay, so oxidation is losing. That is done by these cations. Okay, now the other one then, reduction, is going to be the opposite, and that's when an atom gains electrons. It's weird, it's backwards, I know, sorry. So reduction is actually gaining electrons. That's done by anions. Because these definitions are a little bit weird, I'm going to give you a quick trick. We are going to write down oil rig. Okay, so if you can remember oil rig, then you're going to be good. That stands for oxidation is loss. Oil, O-I-L, oxidation is loss. Rig stands for reduction is gain. So if you can remember oil rig, that will help you remember what's oxidation, what's reduction, okay? Now, remember that oxidation state that we talked about just a minute ago? The reason that's so important is that tells you how many electrons got lost or gained. So +1 means that we lost 1 electron. +2 means that we lost 2 electrons. So we're going to go through all of the different areas of the periodic table and figure out what's really happening so that these atoms can become ions and obey the octet rule. So everything in group 1, we said, makes a +1 oxidation state. So remember, the name for group 1 is alkali metals. So they're metals, okay? And so up above, we said that metals are going to lose electrons in oxidation, all right? Because it's a +1 charge, that means that they're going to lose 1 electron. And when that happens, they'll be happy and have their octet. So here is Na, that's in group 1. If I put a dot, that shows me that 1 valence electron that it has. But oxidation means that that electron is going to go away. It is going to get lost. So we drew that dot and we're showing up. Now it's gone. That's oxidation. It becomes an Na +1 ion, and now it obeys the octet rule and is very, very happy. All right, let's look at the next group. If we talk about group 2, everything there has an oxidation state of +2. The name for that special group is the alkaline earth metals. So again, both of these we're dealing with metals. Even though they have special names, they're both metals. And because they're still metals, we're still going to do oxidation, but now we're going to lose 2 electrons to get our octet. Okay, so here is magnesium. I'm going to show you the 2 valence electrons that it has. Those 2 electrons are both going to get lost. That's the process of oxidation, and so then the magnesium will be an ion obeying the octet rule, and that will be very happy. Okay, the middle of the periodic table is really weird. Those are those tricky transition metals, okay? So, because they're metals, they are all positive, right? We know that this is the transition metal area. Metals always become positive cations. The actual number of, is it +1, is it +2? That's going to change. So the number there is going to vary, but it has to be plus something, +1 or +2, whatever, okay? So, because they're all metals and they're all going to lose electrons, all of them do oxidation. The actual number of how many is going to depend on the periodic table. So maybe you didn't notice this, but if you look at a lot of the transition metals, it says in the corner +1. The oxidation states are there for you because you can't memorize them. You don't need to. We'll give them to you. What you need to understand is, what does that mean? So because I see silver right here with this +1 oxidation state, that means that plus it's losing electrons, and the 1 tells me that it's going to lose 1 electron. When it does that, the silver is going to be a happy ion that is obeying the octet rule. All right, if we keep going with the main groups and back to our normal pattern, group 13 has a +3 oxidation state. We know that. And so there's no special name here, but these are all metals except for boron. Boron is a moron. Boron hangs out with all of these metals, but it's actually a semi-metal. It's so silly. It acts like a metal in this case. So even though boron is a semi-metal, it still has a +3 oxidation state like all of the other metals that are in its group, okay? Because we have metals, we're undergoing oxidation again. The +3 tells me that we are oxidizing. We are losing 3 electrons, and that's how the element is going to achieve its octet. So here's aluminum in that group. I'm going to show you the 3 valence electrons that it has. Those 3 valence electrons are all going to get lost. That way the atoms will be happy. They will have 8 valence electrons. They will obey the octet rule. Okay, here's the tricky group, group 14. That's the one where it says +4 or -4. So how the heck are you supposed to know this? Okay, it all depends on what kind of element you have. So some of the things in that group are metals. Okay, the metals are the +4 option, right? Metals become positive. So these metals are the +4. Whenever you have a positive cation, they're doing oxidation. So a metal is going to lose 4 electrons to achieve an octet, okay? So here's an example. Sn is tin, and so I could draw its 4 valence electrons there. Because tin is a metal, it's going to lose all 4 of those electrons. Then it will have its octet, it will be an ion, it will be very happy, okay? So a metal in that group will be the +4. Now, the other thing that can happen in that group is we have some nonmetals, and then there are a few tricky semimetals. Semimetals act like nonmetals. So if you see a semimetal, except for stupid boron the moron, semimetals pretend to be nonmetals, okay? So we're going to kind of lump these nonmetals and semimetals together. They're all going to do the same thing. We know that nonmetals gain electrons. Okay, so nonmetals and then the semimetals, copy them, all do reduction. They gain electrons, and that's how they achieve their octet. So here's carbon. It's a nonmetal. And so carbon has its 4 valence electrons. It wants to have 8 valence electrons. And so for carbon, it's actually easier to add 4 more electrons. So these X's show the electrons that I added. So by gaining these 4 electrons, now I can see 1, 2, 3, 4, 5, 6, 7, 8 around carbon. It has an octet and it's very, very happy. All right, let's keep going. In group 15, this is where our pattern switches. Now our oxidation state is -3. This is a group of nonmetals. Because we have nonmetals, they are going to do reduction. They're going to gain 3 electrons, and I know it's 3 from the -3 oxidation state. Once it gains 3 electrons, it will have its octet. So let's look at that. Okay, so we have phosphorus over here. Here are the valence electrons phosphorus already has. I've got 5. If I just add 3 more, then I get the 8 to make an octet. So I'm going to add 3 electrons. Gaining 3 electrons makes phosphorus very happy, and now it has its octet. All right, next we're going to do group 16, very similar, except we have a -2 oxidation state. We're still dealing with nonmetals here, so we're going to reduce. We're going to do reduction by gaining 2 electrons. That will achieve the octet. So our example here, we're going to look at sulfur. Sulfur has 6 valence electrons. All I need to do is pop 2 more electrons on there. And now, by gaining those 2 electrons, sulfur has a very happy octet of 8 valence electrons. Almost done. Okay, next we have group 17. The oxidation state there is -1. We are still dealing with nonmetals, but this has a special name. These are our halogens, okay? Halogens, remember, are nonmetals. Because they're nonmetals, they're undergoing reduction, so they're gaining an electron. That will help them achieve an octet. So if I look at chlorine in that group, we have 7 valence electrons. We just need to grab 1 more. By gaining 1 electron, right there, chlorine now has all 8 valence electrons and is very happy, okay? Now, let's talk about group 18. Group 18 has an oxidation state of 0. These are the cool kids. These are the noble gases. Because their oxidation state is 0, that tells us they didn't do anything. They didn't do oxidation or reduction, and that's because they already have a full octet. So this is the Lewis diagram for argon, a noble gas. I already count 8 valence electrons, which means I don't need to add or lose any. I am just very happy. I have my 8 valence electrons, and I can go on with my noble gas day. All right, you did it. Good job, guys.